In this video, we'll be discussing the reactance of capacitors and inductors. Reactance versus resistance. Reactance and resistance are very similar as they both oppose the flow of current. However, resistance results in a loss of electrical energy as the energy is dissipated as another form. In reactance, instead of energy being dissipated as a current flow is opposed, energy becomes stored. As an alternating current passes through an inductor, which is a coil of wire, a magnetic field is induced, where electrical energy becomes stored as magnetic energy. As per Faraday and Lenz's law, the change in magnetic field as current alternates creates a voltage that opposes the current, aka the back EMF. As current alternates, the back EMF will either oppose the current as it increases or will assist the current in its direction of travel if it decreases. This behavior of the current being opposed by the back EMF is the inductance reactance. The opposition of the current flow is governed by the equation where the reactance of the inductance equals 2 pi times frequency times the inductance. The more that the current alternates over a period of time, which is the frequency, means the greater the inductance reactance is. The work done by the back EMF to resist the increase in current is stored as magnetic energy. As current decreases, the stored magnetic energy is converted back to electrical energy and returned to the circuit. The behavior of voltage and current when an inductor is present is represented by this voltage versus current graph as pictured. Voltage leads the current by 90 degrees, as voltage must increase first to overcome the back EMF before the current can increase. This relationship is described as voltage and current being out of phase. Capacitor reactance. As voltage in an AC circuit increases, electrons will be applied to a capacitor and will build up on one plate. This plate will become negative, where electrical energy is stored. This is the charging process for a capacitor. A voltage across the plates in the capacitor will then be created and will oppose the direction of voltage from the power source. This opposition of voltage affects the amount of current that can flow through. As the voltage decreases, the other plate releases some electrons and becomes positive. Energy is released. This is the discharging process. Capacitor's voltage during this stage also opposes the current flow. In an AC circuit, voltage is constantly reversing, therefore this process of charging and discharging constantly repeats. The capacitive reactance is the act of the capacitor's voltage opposing the flow of current. This is given by the equation where reactance equals 1 over 2 pi times the frequency times the capacitance and is measured in ohms. Therefore, as the current alternates fast over a period of time, the capacitor reactance decreases. The behavior of current and voltage when a capacitor is present in a circuit is demonstrated by the voltage versus current curve. Voltage lags 90 degrees behind the current as it takes time for the voltage to increase on each plate of the capacitor, where the current just passes straight on through.